Hey there. I'm just going to do sort of a quick video here because I don't think this one's actually particularly difficult once you sort of understand the secret behind it and remember a few things that you may have forgotten. Um, so this is suppose a scientist wants to create a pool of RNA molecules that are 40 nucleotides and contain every possible combination of bases. What mass of RNA nucleotides is needed to synthesize the pool of RNA molecules? And then it has a little box to fill in that's in kilograms. So at the end, you're going to have to get in kilograms. Okay, so the first thing is there's a little bit of stats that needs to happen here. And so we have 40 nucleotides long. We have to think of how many nucleotides there are, which there's 4 that it could be. And so statistically, the number of molecules you would need to do this with, to get every combination, would be 4, the number of different types of nucleotides it could be, to the 40th power, the number of positions you would fill. And so that would give you the total number of molecules you would need to make every combination that is 40 molecules long, or 40 nucleotides long. And that is 1.21 times 10 to the 24th molecules. Now, as you may remember from your lower level chemistries, pretty much everything we always have to do for calculations is going to be in moles. And so we need to get our number of molecules into moles. And so we have 1.21 times 10 to the 24th molecules in this case. We're going to divide it by Avogadro's number, which is 6.022 times 10 to the 23rd, and that's going to give us the number of moles. And you can set it up like this so that molecules cancel and you get moles out. And so this will be the number of moles of our RNA polymer we need for this specific version of the problem. Remember that the numbers in these are always going to be a bit randomized. So we have 2.01 moles of the RNA polymer. The next thing you're going to do is to get into mass, you're going to need the molar mass. And so we get the molar mass of a polymer, and that's going to be of one RNA molecule, and that would be 330 grams for 1 mole of a nucleotide. And don't forget, this is 40 nucleotides long. So one of these polymers, which you have 2.01 moles of, is going to be 40 nucleotides long. So you have to multiply it by 40. You then are going to take the molar mass, that's 330 grams per mole, and you're going to multiply that by that molar mass, that 330. And then finally, you're in grams, but you want to be in kilograms. And so what you have to do is you actually have to divide by 1,000, because that's the number of grams that would be in a kilogram. And this is actually wrong right here. This should have just been a G. That's funny. Okay. Anyways, so that ends up being 26.5 kilograms for this problem. Now you may wonder, one of the questions I see people ask me about these things is, Dr. Clausen, why can I just use a single number here? There's multiple different nucleotides. Well, the answer to that is we're using a number that the number of significant figures, this last digit is where you would round for the difference in those nucleotides. So really we're using an average number for the nucleotides that just encompasses in its significant figures in the level of accuracy the difference between the nucleotides. And so on average this will be the number, but keep in mind this is only 0.1 kilograms accurate. That's a lot of mass as far as nucleotides go. Okay, let me know if you have any issues or if you don't understand anything. You take care now.